Hello. Today is the new day to make some progress. Let's go on with problem 37. Truncatable primes. So this number has an interesting property. It is prime, and also, while we remove digits from left to right, it remains prime. And similarly, from right to left, it also stays prime. We need to find the sum of the only 11 primes that are both truncatable from left to right and right to left. Okay, to do that, I think we will simply use a standard algorithm for checking primality. Actually, I think these numbers shouldn't be very long, so we can simply use Eratosthenes sieve. If only could I remember in which file it's written. Oh, 35, okay. Actually, I'm starting to think about making a library for solving this. Okay, actually it's fine. So let's copy this. Actually, before copying, I'd like to create new file here. We rename it as 0037. We create a new file here, which will be empty. Okay, and here we create a new project. And we switch the running project. Now here we need to copy this Eratosthenes. Let's call it Eratosthenes. And here, this will be the constructor of this class. So actually we say that here we construct this class. Here we remove this part. Here we don't return anything. And this works quite well. We don't need this part. Finally, we can find answer which doesn't have any arguments. We simply print find answer. Here we use 37. Nothing here. And let's go. Actually, it will be a vector of ints. Ah, no, it will be int. Yeah. So how do we do it? So I believe what we really do is so we need to check if this number is truncatable. Yes? So let's check that a number is truncatable. So first of all, let's start with going from right side. So int m equals n, while m, we need to check that it is prime, and to do that we need our sieve. So we have also a static sieve. And we would like to... Okay, actually, let's create some bound like 1e6, and we hope that there are no numbers which are greater than 1e6. Great. So while m, we do the following. We ask, is it true that m is prime? So if it is prime, if it is not prime, then we need to return false. Actually, it's bool here. So if it is prime, we divide it by 10. Great. What next? After that, we would like to find the number of digits in this number. Let's calculate it. To do it, let's simply store it in number d, and each time we divide m by 10, we increment d. Now we can do the following. So we have a power of 10, which is initially 1. In the cycle, we multiply it by 10. And we check that m% is prime. And if it is not, we have to return false as well. Nice. In the end, we return true. Okay, and in the find dance, we also have this number n. We go through all numbers from 10 to n and check if they are truncatable. If I is truncatable, then ans plus equals I, and it returns. And also, I like to print this number just in case. Okay, let's look at these numbers and these numbers. No numbers? No numbers. It seems like there are zero numbers. However, I don't think that it's correct. Okay, it can be correct. It can be correct. We simply need to find an error. Because it should be n here. Of course, when I look at m, m is 0 already. Okay, now it works, and we indeed found 11 numbers. Okay, we can remove this part and return this answer. Yes. Okay, let's go on. So we take number 192, and we see that its multiples cover all digits. And this number is called the concatenated product. What is the largest 1 to 9 pan-digital 9-digit number that can be formed as the concatenated product of an integer with 1, 2, etc. n? Okay, this is quite easy, although again not really interesting. So we continue this process. Remove this, remove this, remove this. We create an empty file, which we will not need again. Let's look here. So we need to find the maximum pan-digital number. To do that, we would like to iterate over all possible numbers. Okay, see, since n is greater than 1, it's easy to see that you cannot have, so n is at least 2. And this means that in the minimum number, in the first number among these, you should have at most 4 digits. Because if you have at least 5 digits, then in the next number you also have at least 5 digits. So actually, you only need to iterate over numbers from 1 to maximum 4-digit number, which is 9,999. So what do we do? So let's write a function get pan-digital I, which returns 0 if you cannot get a pan-digital number, or it returns this pan-digital number if it is possible. Then we say that answer is maximum of answer and p. And then we return answer. So let's write the function get pan-digital. Write the function get pan-digital. Okay, to do that, we need to do the following. First of all, we start with an array of used digits, which is initially empty, which is initially only falses. So this means that we used none of the digits. Also, let's say that the 0th digit is already used, so we cannot use it again. And finally, we say that number of used digits is 0 initially. Then we would like the following. We would like to iterate over all numbers. Okay, so number of used is less than 9 plus I. Actually, let's start with n. It will be even nicer. And we say that I plus equals n. Okay, here we need to say that we use number I. So actually, function use, there will be a function use, which takes a number, stores its digit in this array, updates this number of used, and if something strange happened, for example, we have a digit which we already saw, then this number of used becomes infinity. So it becomes greater than 9 and we break. So here Actually, let's also make this function use. It should return the length of this number k. Okay? And also in the number uns, we store the concatenation of all these numbers. So if in the end uns is if in the end number of used is 9 is equal to 9, then it was a correct pan-digital number and we can return it. Otherwise, we return 0. Let's do it in ternary fashion. Extraordinary. Here we need to store the number of digits in I. Then our answer should be multiplied by 10 d times. And after that, uns plus equals I. So we have concatenated number I. So now the only thing which we need to do is to store in this use function. So this use function should store necessary truths in this area used, and it should return the number of digits. So let's start with the number of digits. So while k plus d, k divided equals 10, and we return d. So now it does almost exactly what it needed to do. However, we also need to work with used. So let's look at the last digit. And if it is already used, then we return, well, like say that number of digits, number of used is 1 in 9 and return 0, for example. However, otherwise we simply say that it is true now and plus number of used. So it seems like it should work. Let's check what it says. No. What's wrong with you? Find ans? No, it shouldn't take anything as an argument. Okay, it's output something very funny. Okay, what does it look like? It looks like this number and then it is doubled. Yeah, it definitely looks like a number and a doubled number. Excellent. Let's go on. Problem 39. So P is the perimeter of a right angled triangle with integer length sides. ABC. And there are exactly 3 solutions for P equals 120. For which value of P, at most 1000, the number of solutions is maximized. Well, there is a way to do it with jump cycles, but let's actually pretend that we want to do something with Pythagorean triples. So if we have a Pythagorean triple ABC, it's well known that actually you can maybe swap these numbers a and b in such way that a becomes 2kl, b becomes k squared minus l squared, and c becomes k squared plus l squared. To prove that, firstly you eliminate the maximum common divisor, then it's easy to prove that this number is odd. So you choose a in such a way that it is even, then it's kinda easy to prove that c minus b should be square, should be double square. And then, okay, let's actually prove it. So I take c squared equals a squared plus b squared. This means that a squared is c squared minus b squared, which is c plus b times c minus b. Problem is this number is, both these numbers are odd, and this means that both of these numbers are even, and there is at least one of them which is not divisible by 4. For example, this one, it is not divisible by 4. So 4 does not divide c minus b. And this means, but 2 divides c minus b. So this means that these both are not squares. This is not square and this is not square. Why they are both not squares? Because one of them is not square because of this power of 2, and the other one is not square because their product is a square. If you have a square and it is a product of x squared times some y, then y is also a square if it is not 0. And the problem is we already have one non-square, but the product is square, so the other one is also not a square. So they both are not squares. However, you also know that the GCD of these numbers, GCD of b plus c and b minus c, is GCD of, let's subtract like this, we get 2c and b minus c. Okay? So, and this number divides GCD of 2c and 2b minus 2c, which is simply GCD of 2c to b, which is GCD of c and b times 2, which is simply 2 because these numbers are relatively prime. So 2 is divisible by this number. So this number is either 1 or 2. We already know that both b and c are odd, so they should be, so this GCD is 2. This means that if we divide both of these numbers by 2, they become relatively prime. If we divide a by 2, it becomes, if we divide the left part by 4, it becomes also a square. So now a square is a product of two relatively prime numbers. This means that they are both squares. So this means that c minus b over 2 is apparently x square, and c plus b over 2 is apparently a square. And this is of what these k and l stand for. So k is simply a square root of this number, and l is a square root of this number. So now we know this representation, and we look at the perimeter of this triangle. The perimeter of this triangle is simply k squared, 2k squared plus 2kl, which is 2k times k plus l. Great. So we need to find the number of ways, the number, so for each number p, like, we can take So first of all, the perimeter should be even. So let's divide it by 2. So P over 2 is K times K plus L. And you simply need to take any such numbers K and L so that this product is definitely this product. And also K should be greater than L. If you want this to be a non-degenerate triangle, you need K greater than L and L greater than 0. So two integers like this. And besides that, there are no restrictions. So this means that actually you need K times some number which is less than 2K. That's all you need, but greater than K. So A times B, where B is between A and 2A. This is what you need. And this number of ways is what you get. Well, since we have P at most 1000, let's simply iterate over all possible K and L's. This is the easiest thing that we can do. Okay, let's go. So we start with, oh sorry, cancel. I actually would like to duplicate this file. So we store this number n. Actually, this time we have an interesting input, which is 1000. Great. And we iterate over all possible numbers. First of all, the perimeter is even, so... Okay, so first of all, let's iterate over all possible L's. An interesting part is that minimum K is simply L plus 1. So if minimum K times L is already greater than N, then we need to stop. So we need to break. Otherwise, we go through all possible Ks. Such that K times L is at most N. Actually, 2 K L is at most N. Actually, no. Here we should write like minimum K plus L. So like this. And we increment answer for 2K K plus L. Then we find the maximum possible answer, which is max element of answer.begin, answer.end, minus answer.begin. And we return it. To do that, we also need this vector int ans, which stores the answer actually. So here we need to look at n plus 1 numbers, and it will store the number of ways which we are interested in. So if we wrote this, this would be this number of ways. And we can actually print it. But we are interested in the problem, we are interested in the number which reaches this number of ways. So this function works like in n square root of n times, something like this. But also it takes linear space. I am actually sure that you shouldn't need such a lot of space, so much space. But who knows? 240. 240 is said to be the maximum. Is said to have maximized this number. Does it make sense? Let's see. It says that it has two ways. No, two ways is not correct. It cannot be that only two ways. It cannot be that there are only two ways. So we have 2k, k plus l, and there are only two ways. No way, it cannot be. Why only two ways? There are exactly three solutions for p equals 120. Hmm. Now I don't have an idea why it doesn't work. Why it doesn't work? A is greater than L and L is greater than 0. Because we need 2 here. Yes. Still no. Can we get a greater number if we increase this? It really seems strange. It cannot be 4. Only 4 for 5040. So first of all, for example, here, let's look at this thing. So here we have 48. Yeah, let's take 20, 48, and 52. 20, 48, and 52. So this has a greater power of 2. So obviously and clearly this is 2kl, so kl equals 24. Now we know that these numbers are k squared minus l squared, and this is k squared plus l squared. Let's add them up, and we see that k equals 6 and l equals difference between these numbers over 2 and square root. The difference between these numbers is 32. Over 2 is 16 and square root is 4. So k equals 6 and l equals 4. Yes. Now, so it should, when it looks at l equals 4, which it should, yeah, let's take l equals 4. L equals 4. Then minimum k equals 5. 5 times 9 is not greater than n, so we don't break. Then, starting with min k, it checks this number 2 times 6 and x 6 times 10. Some moment. It becomes 120 and it increments the answer. Okay, I don't know. Why doesn't it work? What prevents it from happiness? So L equals 4. So now nth 120 should increment. Why is that? Because this number is 120. Now it's 1. Yes, however, there are 2 more answers. Let's look at them actually. For example, 24, 45, 51. So 24, 45, 51. So here, clearly, this is the interesting numbers. And we see that... I get it. I was wrong. I was wrong all this time. Because actually you can multiply it by a number which is free of squares. So you either can multiply it by any number, but k and l should be relatively prime, or they can be not relatively prime, but you should multiply it by a square-free number. Okay, this is kind of problem. This is a bit problematic. Still should be fine. Okay, to do that, let's find the set of all possible square-free numbers. Till number n, for example. So if it is square-free, then we push back it in square-free array. Then in the end, we also go through all numbers here. And we check if this number is at most n, then we increment this thing. Great, so let's check that something is square free. To do that, we need to go through all numbers from 2 to square root of n and check, is it true that n is divisible by I times I? Then return false, else return true. We could go through only primes here, but it would make it even slower and we don't want it. Great. Okay, now it's clearly should make more sense. So 13. 13 is nice. 13 is nice. Answer is 840. Let's go on. An irrational decimal fraction is created by concatenating the positive integers. It can be seen that the 12th digit of the fractional part is 1. We need to find this digit of this thing. Let's go. Let's actually go. This is quite straightforward. So, however, well, I can just do it in fast and easy way, but there is also a right way to do it. Since there is also a right way to do it, let's do it right way. Or not. Maybe it doesn't worth it. Okay, as an input, let's give it all these digits and the number of these digits. So it is 7, and these are the numbers of these digits. So here we read actually I don't want to do it the fast way. Let's do it a straightforward way. So let's start with sorting it. Then we go through. So what do I want? I want to store the number of digits which we have already processed, which is 0, and the last number which we have looked at. Which is also 0. Then let's go through all numbers. So first of all, we want to look at the number which contains this digit number I. How do we do it? So maybe last number already contains this digit I. How do we check it? We can check it by looking at this number of digits. So while digits is less than I, we need to do something. Okay, now digits is at least I. This means that I is contained in this last number. To find the actual digit, let's take m equals last number, and int k equals digits. So while k is greater than I, let's do the following. M is divided by 10 and minus k. So now k equals I, and this means that the number digits, the number k No, the number m. Its last number is what we need. We also store uns, and we can multiply uns by m%n, and we return uns. So now we need to do something here. So digits is less than I. Then we need to increment last number, and we need to concatenate this last number with what we already have. To do that, we simply need to add the length of this last number. It can be done like this. So we take toString of last number, and to do that we need to include string. And actually I would like to have this line in my template. ToString of last number dot size. Finally, we need to take 40th file here and 40th file here. That is 210. Okay, let's believe it. Why not? Okay, problem 41. We shall say that n-digit number is pan-digital if it makes use of all the digits from 1 to n exactly once. This is 4-digit pan-digital and it is also prime. What is the largest n-digit pan-digital prime that exists? Okay. So actually, we will also apply some brain here. Let's look at this number. So this is definitely not prime. It is not prime because this number is divisible by 3, this is also divisible by 3, and this is also divisible by 3. This means that the sum of all these digits is actually divisible by 3. And this means that this number is divisible by 3. Moreover, however you shuffle these digits, it is still divisible by 3. So you cannot have any 9 pan-digital number. It doesn't exist. So the best hope is for 8-digit number. And I'm quite sure that it exists. To find it, however, we would like the following. So let's assume that this fact is given as an input. So as an input we have number 8, which means that we need maximum 8-digit and digital prime. So we need maximum n-digit pan-digital prime. To do that, let's start with maximum possible prime, which is 8, 7, 6, 5, 4, 3, 2, 1. Then we start iterating over all permutations in decreasing order. So this is the maximum possible permutation, and we go through all of them in decreasing order, and we check each of them for primality. So since this number is not divisible by 3, I quite believe that there should be at least one prime. It's not always the case, maybe. For example, if you have only 1-digit 1. Oh, I was wrong. I was wrong, of course. This number is also divisible by 3. See? Because this is divisible by 3 because, well, you just removed 9, and 9 is divisible by 3. But actually, the best hope is 7, not 8. So we start with 7-digit number. We iterate over all permutations in decreasing order and check each of them for primality. Okay, we start with 7 actually. 7 I said. So let's go. So we take vi v n instead of vi we should take vector int. Then we go through all numbers. So like while true, I guess. So we calculate this number. So what do? We just say that number equals number times 10 plus I. And if is prime number, then we break. Actually, instead of this, we could do like this and like this. So we break if it is prime, then we return this number. And here we need to take the previous permutation. How do we do it? Maybe there is just a function. Yeah, there is a function prev permutation, and we apply it to v.begin, v.end. The other possible way was next permutation. No, actually, there wasn't such way in that set. I thought that we could write next permutation of v.r begin, v.rend, but it is incorrect. Okay. Now we only need to check for primality. And we do it usual way in square root of n time. If n%i equals 0, return false, or else return true. Also, if n is at most 3, return n is at least 2. Yes. Let's choose this and let's choose this. It took less than a millisecond and we finally found this number, which is probably prime. Okay, problem 42. The nth term of the sequence of the triangle numbers is given by this formula. By converting each letter in a word to a number corresponding to its alphabetical position and adding these values, we form a word value. If the word value is a triangle number, then we shall call the word a triangle word. Using these words, how many are triangle words? Okay, let me think. So how did I do it the previous time? The previous time I converted it into a txt. Let's do it again. So I have the problem 42. Let's actually put it here. Okay. Okay. So how do we check if a number is triangular? Actually, I have a problem. Are these words short? They're common. First, if there is a long enough number, then this is not really nice because it might overflow my type. I would like to do the following. I would like to say that since a times a plus 1 over 2 is my number k, then a times a plus 1 is 2k. So it is there is a solution to this equation. And this is equivalent to this having an integer root. Integer root has the following formula: minus 1 plus minus square root of 1 plus 8k over 2. So we simply need 8k plus 1 to be a square. It should be a square. So there are several challenges. First of all, we need to check if a number is a square. Okay, this is kind of standard. Let's do it. Let's simply do it. Okay, so let's make function. Let's make function is a square. And to write this function, we'll need another function which finds an integer square. Let me think. We need a function int I sqrt. No, I don't like it. Let's make it unsigned. So then, if we want to check if a number is a square, we simply find its square root. And check that x times x is n. So now we need to write this function. How do we check that? How do we find it? Let's find some answer, which is square root of n in double. Let's actually do it in sqrt L. Then, so what do we have now? So this is our number line, this is our number n, and x squared is somewhere. So there are three cases. It can be here, it can be here, and it can be correct answer, or it can be here below the correct answer. Okay, firstly, I like every number to be this one, and then I can increment it. So let's do it. How do I make a number strictly less than hmm. So what do I do? Okay, let's make an easy thing. So if n is at most 1, then we return n. This is an easy one. So if we have some square number, okay, no, maybe we want it to be in this category. We want to eliminate this category. This category is only possible if x is greater than if n squared, x squared is greater than n. Okay, so to check that, let's do something like this. Let's take the limit of unsigned. Well, as well, I can make it u in 32t and here u in 64t. I believe it's better. So this is the maximum number which can be stored in this type. So and I can use UL here as well. So while p is greater than this number, or p times p is greater than n, I need to subtract 1 from p. Well, no, I think it's easier to, first of all, move into this area, and then move into this number. So this will finish our solution. So here we will return p. But before that, we want to make p at least I squared tn. So this is our goal. To do that, let's actually move it up. So to do that, let's say while p is less than this number, actually I can write it like this. While p minus 1, actually p plus 1, I think. P plus 1 is less than this, and p times p, while it is strictly less than n, I can increment p. Then I need to decrement p and I return p. So it can be slow if n is really huge. So it works in something like maximum of int64 divided by multiplied by the error of a long double type. But we think that it will work fine. It shouldn't take long. At least it always gives the correct answer. Okay, now we can check if the number is square. Then we can move here. Oh, let's check that the number is a triangular number. To do that, we need to check that 8n plus 1 is a square. Finally, let's go through all words. To do that, we would like to look at them. So they look as a list of words separated by comma, and there are also quotes. Let's do it. Actually, I have already done it. I don't remember. Okay, it's actually easier. Let's find the previous problem with a dictionary, and we can see that it's here because of the size of this file. So we need 22nd file, and yes, there was this function parse to vector, which we will copy. It simply takes this string of all words and it converts it into a vector. And we also need, well, we need this part. We need this part, and we need, no, we need this part. And we need this part. Okay, let's go on. Oh, we also need an alphabetical value, so this is handy. Alphabetical value. Okay, so we need to find the number of triangle words. So it's easy. Let's take answer. Let's take all words, and if is triangular of, actually I also want them sorted just for debug reasons. Let's print this number, this word t. It's funny that I also always return int, although it can be long maybe. Let's make it long. So if number a is a triangular number, we print t and actually a, and we increment answer. After that, I'd like to return the answer. What's wrong here? Ah, okay, let's go. There are a lot of words here. For example, sky is a triangle number. Let's check it. That sky is indeed a, yes, it is triangular. Ah, it seems because I was wrong about what is a triangular number and what is alphabetical number. Oh, indeed, int is enough. Okay, let's remove it and remove it. And we get the answer, which is 162. Okay, this number is 1 to 0 to 9 pan-digital, and it also has a rather interesting substring divisibility property. Let d1 be the first digit, d2 the second digit, and so on. Then each next of these numbers is divisible by next prime. Find the sum of all 0 to 9 pan-digital numbers with this property. Obviously you need to go through this array from end to the beginning, because it's really much harder to be divisible by 17 than it is to be divisible by 2. So we would like to start with divisibility by 17, and then in the end, we check the divisibility by 2. Okay. Okay, let's do it. This can be done with a straightforward actually, since these numbers from 2 to 17 are given in the input, let's just put them in the input file. So I am interested in 7 numbers from 2 to 17. Save and save. Also, let's give this number actually, let's give 2 numbers. Let's give number 10 number 3 and number 7. So I is from I is from 0 to so we need to read 3 numbers. The number of primes, the number of consecutive digits, and the length of the number. So here we need to return ans of, what do we need? We need to print the sum of all pan-digital numbers. Okay, I think it can belong long, but maybe not. So PKM. const int k, const int m. Let's go. So we have this. Okay, we have a number, and if we take k last subsequent digits, then they are divisible by, then they divide, they are divisible by p last, which is pn minus 1. So let's like store the permutation of all digits. Vector int digits of size 10. Let's go through all possible digits. Or through all possible numbers. Okay, initially it's something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now we want the following. Actually, it will be the digits from right to left. So this is how it looks like in the beginning. Can the number end with 0 actually? It's not obvious from the statement. So I don't understand. Is it can we have a 0 g1 equals 0? We don't know. Okay. We will have to have a wrong answer possibly. So let's assume that you can here have 0 here. Then it's quite straightforward. So what do? We have some permutation. Let's check one by one all triples of digits. We start with this one. We find this sum. And we check if it's divisible by 17. So if it is not, then we have to unsort these digits. And actually we know that they already sorted, so we need to reverse them. We simply need to reverse them. After that, we need to take next permutation. Okay, so let's go. We need to check. So while true, we need to check n conditions. We need to check n conditions. So actually starting with the last one. No, let's start with the first one, but they are numbered in reverse order. So we need to check that something pn minus 1 minus I divides something. So let's go through all digits from 10 minus 1 minus also let's store int violated equals n. N means that nothing was violated. Actually, we can actually write it like this. So violated is the number of violated condition. So let's start with digits. No. With digit number violated. J less than violated plus K and plus J. And we need to take sum plus equals digits J. So now if sum is not divisible by this prime, then we have to break. Now if violated is less than n, then there was a violation. What do we do if we found a violation? In this case, so for example, this position is violated. This position is violated. Then, first of all, we need to reverse these digits, which is done as reverse from reverse digits dot begin plus violated plus k and digits dot end. After that, we need to next permutation of digits dot begin and digits dot end. But if we failed, then we need to break from the cycle. Extraordinary. However, if it is not the case, then we have found a number. So we have found a number. Then we need to print it. We need to add it to the answer. So let's first of all calculate this number. So we have found this number. We need to let's like print it in CR. Let's add it to the answer. And also I would like to find the next permutation. What do I do? So I have some number. Last n digits is this number. So I need to reverse these digits and then take next permutation. Let's do it. I need to take reverse of digits dot begin plus n to digits dot end. Then I need to next permutation. And again, if we were unable to take the next permutation, then we need to break. And finally, we return answer. No. We were unable to read the numbers. Okay, this sounds reasonable. Okay, not many of them, but we didn't break from the cycle. Also, why are they so short? What is n? Ah, I need m instead of n. If this makes sense, okay, now I have a lot of numbers, but this is not good. This is definitely not good. Why is this number negative? This number is negative because maybe this was too big. Yeah, you don't have any problems here. Why is it sometimes negative? For example, this one. Why was it negative? Ah, 10 digits is maybe 10 to the power of 10. Okay, yeah, we need long. We need it long, that's it. Otherwise it's fine. Otherwise everything is fine. Okay. Actually this solution took not much time. 16 milliseconds only. And in release it would be even faster. So let's check if we have this number. 980. Okay, I definitely don't have this number. I don't have this number at all. Why is that? I have 980, but the next one should have been 982, and I don't have it. And also it said that this is fine, although it's not fine because... Ah, 3-digit numbers. We need to look at 3-digit numbers. So here we needed to look at some other sums. So we needed to start at violated plus k minus 1. J is at least violated. Minus j. And sum equals sum times 10 plus digits j. I was wrong. Okay, now much more sensible. It's funny how it always is 5. Okay, whatever. If it's always 5, then there are reasons why it's always 5. Hmm. 44. Pentagonal numbers are generated like this. Sum of two pentagonal numbers is also a pentagonal number, but their difference is not. Find a pair of pentagonal numbers for which their sum and difference are also pentagonal and the difference is minimized. So the first moment when the difference between consecutive numbers becomes greater than the answer, I need to stop. Apart from that, it's a simple cycle. This is a standard problem with empty input. Yeah, because I don't see any way to have an input here. Don't have input, we don't have input. We need to find the value of d. Okay, let's go. Let's go. So we need to go through all numbers, starting with 1. Let's take a pentagonal number, which is I times 3I minus... Well, let's store them in a vector. They say that pent dot pushback I times 3I minus 1 over 2. Then I need to iterate over... Let's look at like possible, minimum possible difference. Minimum difference, which is 1 in 9. And in the end, we return minimum difference. First of all, let's look at last two. Actually, let's push back starting with 0. I like it more. So if I and pent I minus pent I minus 1 is already greater or equal than min diff, then we need to break. Or even we need to return min diff. It's even nicer. After that, we assume that we need to check all... Okay, let's do let's rewrite something. Okay, first of all, let's write a function add, which adds a new pentagonal number here. It simply says that we need to do this where I equals pent.size. So this was easy. Also, I need a new function extend, which says while and int n. So it checks while pent dot empty or pent dot back is still less than n, I need to add. This is a function extend. Okay, so here, if pent dot size is at most I, then I need to add, or even while. Then, if this is already the answer, then return the answer. After that, let's go through all numbers j from 0 less than I. So we need to check if a number is if a number is a pentagonal number. So let's do it. Check pentagonal. So this is quite easy. First of all, we need to extend. So we need, if it is a pentagonal number, then vector pent should contain this number. So we say extend n. After that, we take lower bound of this pend.begin, pend.end, and n. Then we take this position. We know that it is a number. This function is what makes this function not be not out of bounds. And we return it. We return that it equals n. So this is simply a binary search. Okay, and here we need to check that if ai minus aj is pentagonal and ai plus aj is also pentagonal, and also if aj minus ai is less than min div, ai minus aj, ai minus aj, yeah. What's wrong with you? Pent. So if it's all is true, then we can indeed say that min div is pent I minus pent j. It will work somewhat slower than we would like. To make it faster, let's start with I minus 1, j at least 0, minus minus j. So here, if pent I minus pent j is greater or equal than min div, we can simply break because it will never be less than min div. And here we can say else if this and this, then min div is updated. Okay. Okay. Let's see. Immediately we have an answer which is 1. It thinks that we can start with 0 here. This is unfortunate, we cannot start with 0. So 0 is forbidden. Let's stop at 1 here. See what's happening here? We have already 427 megabytes. This is not good. Maybe I have already some. I have some overflow, that's why it's happening. Yeah, I have some overflow. I have some overflow. We already have a lot of numbers. Let's look at what we have here. Check pentagonal of this number. So now min div, it is still big. This means that actually we have a problem. We have a problem because these numbers are never both pentagonal. For some reason, it's never a pentagonal number. Okay, finally, we jumped here. Now we see that min diff is some huge number. But then we need to continue for like a lot. Yes? So if we want to do it honestly, what? Yeah, something bad happened. I think we have an overflow finally. What? Oh, oh, yeah, we have an overflow. Okay, let's avoid overflow. And to avoid overflow, we would like to use long longs everywhere. Mm-hmm. Okay, now it found it. It found it. So min diff is this 5 million number. And it stopped. So it spent, let's say how much it spent. It spent like 13 seconds. 8 seconds. However, if we turn on release, it works really fast. It works like in 1 second, I think. Even faster. Okay, then we have this number and we can print it. What do people say actually here? What is this? This is... Oh my god! This is Pascal. Repeat until. Okay, this is a way. This is definitely a way to check for pentagonality. It seems that there is no much that you can learn from this problem. So let's go on. Again, we meet triangular number, pentagonal and hexagonal numbers, and we can verify that there are 3 numbers which are equal. Find the next triangle number that is also pentagonal and hexagonal. So we simply we simply iterate over all possible numbers. So here we write 4755. Here we create 45th file. Here we create 45th project. So in this problem, we would like to do the following things. First of all, we need to say that let me think. Okay, let's make function triangular root. So what is a triangle root? So as we know, nth triangle number is n times n plus 1 over 2. So what I want here is triangle root of k is maximum number n such that it calls argmax n such that tn is at most k. So this is what I call triangular root. If you write this function, then first of all we can check if a number is triangle. To check it, we simply need to check that. First of all, we also need a function find triangle. Let's also differentiate between k and n. So k is what we take the root from, and n is the number of a number. So here is k. To find a triangle, we return n times n plus 1 over 2. Here we check that k equals find triangle of triangle root of n. What's wrong with you? Whatever. K. Okay, here we need to find the number. So we want the following. We want x times x plus 1 over 2 be at most k. This means that k squared plus k minus 2k is at most 0. And this means that x is at most the biggest root of this equation, which is minus 1, inequality, which is minus 1 plus square root of 1 plus 8k over 2. So we need to take I squared t of 8k plus 1 minus 1 over 2. And I squared t can be found here. Okay, let's go on. So here I'd like to find, I'd like to go starting with 1 plus triangle root of k minus 1. Check that is pentagonal of find triangle of I and is hexagonal of find triangle I, then we return I. That's it. So we need to find these two functions, is pentagonal and is hexagonal. To do that, we also would like to have functions int pentagonal root and after that we can replace this function with two more, which are is pentagonal and is hexagonal. And also we need find hexagonal as well. Let's go. First of all, find pentagonal. To find pentagonal number, we need to find n times 3n minus 1 over 2. To find a hexagonal number, we need to take n times 2n minus 1. Well, finally we need to write these functions. So let's start with pentagonal root. So n times 3n minus 1 over 2. And 3n minus 1 over 2 is k. So 3x squared minus is at most k. Minus x is at most 2k. This means that 3x squared minus x minus 2k is at most 0. This means that x is at most 1 plus square root of 1 plus 24k over 6. So this is what we need. We need to return 1 plus square root of 1 plus 24k over 6. Nice. Nice. Pentagonal, it was a pentagonal root. Then we need hexagonal root. So n times 2n minus 1 equals k. This means that 2x squared minus x minus k is at most 0, then x is at most 1 plus square root of 1 plus 8k over 4. So we return 1 plus 1 plus square root of 1 plus 8k over 4. Fine. Finally, we need to write 45 here and 45 here. 285. No, we need to return find triangle, I believe. So it says this number I believe we needed to write it like this. And now we have a problem. We have a problem because we didn't have long actually. So let's replace everything with long. And it should be fine. Long long long. Now it's immediately fine, and it found this beautiful number. (46). So Christian Goldbach proposed that every odd composite can be written as the sum of a prime and twice a square. It turns out that the conjecture was false. What is the smallest odd composite that cannot be written as a sum of a prime and twice a square? It is a nice conjecture. It's sad that it's false. But let's go. So no input. How do we do it? To do it, we need to find a lot of prime numbers and a lot of squares. And we need to like make a convolution. Some sort of convolution. Okay. First of all, let's find some eretosthenes. It was at some moment today. Yes, here it is. Dun 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 dun. Right. So we have eretosthenes sieve of size, for example, 1 million. Then let's go. So I would like to go through all numbers. And also let's check that some number is a square. This is also something that I want. So let's check is square. To do it, we simply need to check that k equals n times n, where n is square root of k. Okay, now we need to go through all numbers, starting with 9. Starting with what? Starting with 3. So what we need to check? First of all, if I turned out to be composite, then we need to continue. If it is prime, then we need to continue. Also, let's go through all like what? Let's go through all primes. So if j is greater than I, if j is equal to 2, then continue. If j is greater than I, then break. And let's also say bool found is false, and found is the wanted representation. So if sieve, if like what? If we want to check, first of all, it's I plus equals 2 here. So if I minus j divided by 2 is a square, then found equals true. And here, if we didn't find anything, then we return I as the minimum counterexample. Let's see if we find this counterexample. Let's switch to debug because it's somewhat nicer. As always. We always use debug because it's like low budget Python. 9. What? 9? It can be 9 because it's 7 plus 2 times 1 squared. What? There were no primes? Oh. Okay, let's fix it actually in the previous code because this is something I don't like. Yeah, this is not what should happen. I don't want it to be normalized. Yeah, so we remove this thing here. And now it makes a lot of sense. Fine, let's continue. So now it somewhat should work. So it worked. And it said that the answer is this strange number. It's not surprising that Goldbach didn't find this number because it's not the smallest number possible. A distinct prime's factors. The first two consecutive numbers to have two distinct prime factors are 14 and 15. The first three are these. Find the first four consecutive integers to have four distinct prime factors each. What is the first of these numbers? Okay. Okay. So the input is simply number 4. So this is the first thing. Then I need to make a copy. Let's write a function which finds factorization. Let's call it fact of trivial because it is trivial division. It's called trivial division. So what does it do? It starts with 2. Okay, let's do it the good way, actually. So let's write a function process prime. And it says while n% p equals 0, then n divides equal p and plus plus k. And here we have the answer, which is simply the factorization. Then it says that if k is greater than 0, Then answer dot implies back p k. Then we go. Then we process 2, process 3, int u equals 2, for int I equals p equals 5. Like, let's do it for ul. P times p is at most n. P plus equals u equals 6 minus u. And we process prime p. Then, if n is greater than 1, we for example, let's just place back n1. And then we return answer. So this is a trivial factorization algorithm, which still not that slow, because it only goes through 1/3 of all numbers. Okay, what do we do here? We go through all numbers, starting with 1. And we look at the biggest streak of numbers which are all good. So first in streak is 0, length of streak is 0, and we go through, for example, all longs. So so what do we do here? We factor number I, take its size, and this is a number of primes. And if this number is exactly n, then we would really like to plus length of streak. If it is not, then we would like to say that length of streak is 0 now, and first in streak is I plus 1. And we return first in streak after this ended. Finally, we would like to create one new project here. We would like to rename this input file, and we would like to run this program. Okay, it found something. It found that we need a number. It found that we need a number. What you don't like? Process prime. What's this k? Yes. And we need factor trivial, because we need factor trivial. And the answer is finally... Oh, it took a lot of time. So in release, it takes like 37 milliseconds, but in debug it took a lot. Yes, but it returned the answer, which is simply this nice number. And final problem for today is problem 48. This series equals this number. Find the last 10 digits of this series. Okay, this is a standard problem on modulus multiplication. and modules powers actually. So first of all, we need to write number number 10 and 1010, which means that we need power still 1000 and we need last 10 digits. Okay, now well, there are different ways to do it, but let's simply ask to have GMP. Why not? Why not have GMP if we can have GMP? Okay, fine. There are reasons why not have GMP. Let's try not to have GMP. This is normal. Okay, let's avoid GMP. We don't want arbitrary precision arithmetic. So we assume that n to the power k is not a big number. Okay? In this case, we find ans nk where this can be long, and this can be, okay, these both are ints. Okay, let's go. So first of all, it's simply some modular operations. So we need to find the modulus. Modulus is LL power of k of 10 to the power k. Let's write the function L power. So while b, if b and 1, then answer times equals a, and if b is big, then a times equals a, and then return answer. Great. Actually, the same way we can write a function mod power, which does the same thing, but here it does the following. We use like answer equals, let's call it LL because it uses long modulus. So it is prod LL of ans A and M, and here we have prod LL of A and A. And now we need a function prod LL. Great. So how do we do it? The best way would be to have int 100 to 128. However, Visual Studio is nice and it doesn't have this int 128. That's why I wanted to use GMP. But this is overkill. There are plenty of ways to make a modular multiplication without the usage of int 128. And one thing is if m is less than 2 to the power 57. If m is less than 2 to the power 57, then we can simply use double. How do we use double? We say I want to say that a times b percent m is a times b minus m times a times b divided by m. So this is the formula, where this is a floor function. However, we would like to calculate this function, but we cannot. Again, because we don't have int 128. Let's try the following. A times b minus m times, and instead of floor, yeah, we'll still use floor. But here we use a double multiplication. So we use double a times b over m. The problem with this is that this is not exactly true. So this is not exactly this floor. So this may differ from a times b by several times m. But this is now not a problem, because if the difference between this number and this number is not big, then we can simply do this. And for example, if ans is less than 0, then ans plus equals m, and then return ans. So this is function product, and it is incredibly fast. It is incredibly fast, which is nice. So here, actually, modulus is long. We go through all numbers from 1 to n, and we want to say that ans is some LL of ans, pow mod LL of I modulus modulus, and we return answer. Now we need these two functions. This is already done, and finally we need sum LL, which is simply if a plus equals b is at least m, a minus equals m, return a. That's it. Now we can find the answer. And we will, no, I need 48 here. No, maybe this file might be huge. Let's delete it, and let's look at our answer. It's some 10 digits. It's some 10 digits. Well, we had a good day today. Recently there was this problem 873, but unfortunately I overslept its appearance, because it appeared at 4 a.m. and while I wasn't sleeping, I still wasn't quite adequate at this moment. I wasn't able to solve it. However, this time it's almost okay, so maybe I will solve this problem this time. So we'll try. Thank you for watching. I see you next time.